Okay, so this is where we go. Welcome to the 1B revision seminar. Um, my name's Nicholas. You guys, if you've got questions, ask me. This is the whole point. I am a little bit hard of hearing, so that might mean you have to be loud. But yeah, there's no point in coming here if you don't ask your question, if there's something that's going on. Because the first thing we're going to talk about was sequences or power series and Taylor series. Firstly, possibly some of the terms. So what I've been doing is I need to remember to do this. So if we go that one, share. So it's just looking at the notes about some of these things. And so some of the things that they're talking about here, just so when it says necessary condition for a series for a convergence of a series, they have this thing that says like if some, what are they saying? N is equal to 1 to infinity. So this is what this is actually doing is saying that if my series converges, so if the sums converge, then the limit of the things I'm adding at each step must go to 0. All right. And so we don't actually use that. We go the other way. All right. If you are asked if a series converges, one of the first things you can do is look at that limit and go, if that's not 0, series can't converge. All right. This is actually one of the things people forget to do. There is, because this limit thing here tells me, genius. This is where I go. That's the other thing we're very good at doing. We want to go there. We want to go change to that one. So if the series converges, then this limit is equal to 0. Okay. And so that means that if the first thing I'm going to ask is, does this converge? If my terms don't, if the limit of the terms is not 0, I can know straight away that it's not going to converge. All right. It's like, is it a subspace? The first thing you ask is, does it contain 0? This is the same sort of thing. If I'm asking, does it converge? Is that limit going to be equal to 0? All right. The reason they call it a necessary condition, all right, is that this will happen if a series converges, but it's not it's what they call sufficient. They have necessary and sufficient. Sufficient, if it's a sufficient condition, then it will happen. If this is true, then this will follow. This is just something that will come from it, and we can use it because it's necessary, but it's not enough to guarantee the series converges. So if I'm looking at this, I go, hey, my limit of my terms is 0, then I have to do something else to determine if the series condition converges or not. And so that's where we have various things. Can I do something about it? Is the lighting okay there, or would you like me to try and work out how to turn the lights up? Because I am just room. Wait. All right. Took a while, but that's okay. Okay, cool. That feels better too. So there are other things. So when you think about series converging, what is the first thing you think of? Going to a point. Yeah. So there is a thing that says, so if what? Some AN converges, I probably should check the notes to make sure I get it right, but there exists sort of M such that they do this thing. I'm gonna have they actually put it in here? There's a fancy way of writing it. And I should probably make sure I get it the way you've got it, put it in lectures. Geometric. Oh, no, no, too far. What was that one? Oh, actually. Actually, what we'll do, Sn is equal to sum of An, n is equal to 1, 2. I'm going to make that an I, because that will make my thing work a lot better. All right. All right. This is kind of like, we define it in terms of something else. You know about convergent sequences. Now, convergent sequences, this is where this sort of thing comes in. If so a sequence, we sometimes do this. So sequence of n converges to some number m if there exists delta greater than 0 and n naught, then distance of Sn minus m is less than delta if n is greater than n naught. So it's saying basically beyond some point, my sequence value is within a certain value. Okay, so the next thing we're going to do, right? So those are the really fundamental things that we build on, all right? And sometimes it can pay. I'm really more interested in this. God, sure. Gotta keep on me. Gotta go, Nick. You're not showing the right thing. That one. Where'd it go? No, not that one. That one. That's what we said. That one. Yes. Let me do that too. All right. So we want this one because we're going to fall back to that. The next thing we're going to talk about is the ratio test. And so we're going to go if sort of an plus 1 on an is less than 1, it occurs to me when I'm doing this, what I should have done is gone the other way. That works. I should. Did you ever wonder why this is true? No. Okay, sure. So the reason we're doing this, right, is we go back to the one series we know about, right? We know about geometric series. So sometimes we'll write that as n is equal to 1 to infinity n a times r to the n. Now, if I apply, so we know if absolute value of r is less than 1. Notice how this thing and this thing are saying basically the same thing. Okay. And what that's saying is we're actually comparing our series. So in this case, we're testing the series against what would be equivalent to a geometric series. If in the limiting case, it's like a geometric series, then we know it's going to converge. In actual fact, there's a lot of, when we talk about series, we're less worried about what happens at the front and more worried about what happens at the back in terms of whether it converges or not. All right, because all of these things are talking about limits when the n gets large, right? So we could have something where, in principle, we can just keep on going a little bit at a time. But we know things like, we know the geometric series converges. In fact, we know that this thing, so we know this is that sum n is equal to 1 to n, I think it's actually going to be 0, of a r to the n is equal to a 1 minus r. Seen this thing before? Okay, I would have hoped you would. I haven't checked the notes carefully enough to know that that's in there. That is a thing we know about in geometric series. Yep. Okay. And so one of the other tips is, like, sometimes in the exam they'll go, hey, what is the sum of the series? All right. And so pretty much if you're in 1B, the answer is it must be a geometric series. How do I write it as a geometric series? All right. So one of the questions you had in Maple TA, so that's old school language for it. Mobius, one of the Mobius questions was you get something like what did they do? E to the NC. Something like that. Okay, so you've been given a series, you know it must be a geometric series. All right, you know it has to be a geometric series just because of the way this works out. And so what I would do is I would write that as n is equal to 0 to infinity of e to the c to the power n is equal to 19. And then that puts me into this sort of form. All right. In actual fact, that if we compare sort of this form with this form, that's saying my a is 1 and my r is e to the power c. And so this should be equal to 1 on 1 minus e to the power c. And I'm using that information to then solve for the value of c. Okay? Literally, that was one of your Maple questions. And so then it's just simple algebra to get the value of c from there. Okay? So these are the things we're trying to work with. All right? So when we're talking about a power series is like an extension of a polynomial. All right. So when we're talking about a power series, so we're going to write something like ai x to the I is equal to 0 to infinity. Something like that. Okay. But for any given value of x, this is just a series. And so it has the same ideas, all right? And so the reason we want it, but it comes with a couple of ideas. This thing is actually centered around x is equal to 0, all right? So it's radius, so it will have, if I put in x is equal to 0, I know it's going to converge because everything's going to be 0, right? All right, and if I make x small enough, so all right, so if I make x small enough, then I know my series is going to converge. But then there's the question of, well, how big can I make it before it comes in? And that's where that concept of interval of convergence versus radius of convergence comes into it. All right. And so and again, so this is why I was talking about doing this thing. This ratio test, all right, is going to be the thing that allows us to work that out. All right. If we're going to do this, we're going to go, okay, well, my ratio test, we're going to have something that's going to be like limit n goes to infinity of, so it'll be a n plus 1 x to the n plus 1 on a n times x to the n. And I want that to be less than 1. But just by looking at what's going to happen here, I know that most of that x is going to cancel out. I'm going to have like a limit n goes to infinity of like a n plus 1 on a n times by x. I'm going to break those up, and I want that less than 1. And so this thing here becomes some sort of number. all right? And that's telling me how wide X can be. So I can actually do the thing where I go absolute value of X, it's got to be less than 1 on this limit. Beautiful. That would help. Okay, so I can actually do that to work out my radius convergence. All right, so all good. We've got these ideas. This thing will sometimes refer to that as your R, the radius convergence. Have I used that somewhere else? No, we should be good. And so we can actually work out how big an interval around that point. So Taylor series actually takes this idea and extends it. All right. So there was the Maclaurin series. So Maclaurin series looks a lot like this thing here, all right, because it's centered at 0. Okay, so centered around 0. Taylor series actually went that next step and gone, hang on, I could do this clever thing where I could actually, like when I do an X minus A, I'm centering it around A. And so that's like so whenever I replace X by X minus A in any function, I sort of re-zero it. I think the 0 becomes at A rather than 0. All right, so it's a horizontal translation to the right by A units. So Taylor's gone, hey, we could just do this. This is a nice simple way of doing this. And so we can it will be more useful. All right. So you think about it. I've got a little bit where this thing is going to work, right? It's going to converge to a value. And if I've set it up right, it's going to converge to the value I want. All right. So that's where how do I make it work? Have you actually thought about that? Have you actually thought about what's going to happen? So if we just write out the general, Taylor polynomial. So they say and it's like the nth derivative evaluated at A on n factorial times by X minus A to the n. So this is that horizontal translation that re-zeros it around A. This thing here, if we just go n is equal to 0 to infinity, one of my favorite pastimes with series is to write it out, add it up. Okay, that is, write out the terms. If like with any sum, if the number of elements in there is less than somewhere around 10 to 12, maybe quicker and easier to write them all out and add them up. That might be the easy plan. If it's more than about 6, there's probably a trick. All right, so there's these two competing rules. Less than somewhere around 10, probably you could just write them out, add them up, might be quicker and easier. If it's more than about 6, there is a trick. Okay, so but if we just write out what these first two terms look like, or first few terms, when n is equal to 0, this is f of a, the 0th derivative f of a. When n is equal to 1, so this is the first derivative evaluated at a, and 1 factorial is just 1, so I'm just going to go x minus a. And so if I do that, that's literally a horizontal line that goes through the function value at the point I'm interested. All right, it's not even a tangent. When I include this thing here, this makes it a tangent to that line at that point. So now we've got the function value correct at that point, and also the slope correct at that point. So you can see how my approximation to the function is going to get better. All right, but then we're going, well, maybe I want to get the right curve too. All right, so if I want the right general curve of the function, I'm going to go f double dash of a on 2 factorial, there's 2, and then x minus a all squared. And so this means it's also got the correct value of the second derivative at that point. All right, so now we've got function value is right, the slope is right, but also the general shape of the curve is right. And so what Taylor's polynomial is doing is adding successive derivatives. So we get more and more accuracy at that point, but it's only at that point. That's actually one of the key parts about this. It's only at that point that it's exact. But the more I get, so you know, with a linear approximation, if I've got my sort of function doing a nice curve, if I have a straight line near the point where it touches, it's actually pretty good. As I move further away, it gets terrible, right? As I'm moving further away, it becomes worse and worse. So this is where this idea of, well, how far can I go before it's a bad idea? And with my Taylor polynomial, I can get an idea about doing this. So that's the first thing we're going to do. Now, the thing I remember about doing this, every time I do this, is there are some things. There's a couple of key things we're supposed to do. One of which is we're supposed to recognize certain power series, certain Taylor series. All right, or Maclaurin series, technically. Okay, so we got this idea in mind. We know the Maclaurin series is just where A is equal to 0. We're getting successive approximations working together. Is there any of the actual Taylor series that you know off the top of your head? Okay, so you're thinking about it. I love the idea. Okay, so if I was to do n is equal to 0 to infinity of, and then what is it? X to the n on n factorial. What would that be? All right, so when we're calculating a Taylor polynomial, we're going to have f of x, f of x, f of a. All right, and so I'm going to do e to the x. And so in this case, I want f of 0, and so that would be 1. But f dashed is equal to e to the x. So f dashed of 0 will be 1. F double dash is equal to e to the x. F double dashed of 0 will be equal to 1. Now, if we go back to the form we're talking about over here, if this is always 1 and this is just x to the power n, that would be what my series is. All right. So it can be helpful back in my day, I'm old, you can tell. Sorry about that. I'm going to have to think about not doing that. We were supposed to know some of the series, and we kind of still expect you to recognize some of them. We'd expect you to recognize this is, the Taylor series or the Maclaurin series for e to the x. Taylor series centered around 0. All right. So fair enough. You're good with the plan, right? Yeah. So there are some other ones. Now, so let's try doing the same thing, except for I'm going to start with, say, sine of x. And so the derivative is going to be cosine of x minus sine of x. Did I do that right way? Sine goes to cos, cos goes to minus sine. Yep. Minus cosine of x. And so this is, the thing at 0. And so we're going to get 0, 1, 0, minus 1. We don't need to go any further for you guys to know that it can. So sine of x, the Taylor series, the Maclaurin series, I is equal to 0 to infinity. The first one's 0. And the second, so I've got this wonderful thing where I've got like minus 1 to the power I. I'm going to leave that there because in my mind, I might have to add 1 or take 1 to make it so the sign matches up. All right. But like this thing here is going to work out to be, this is going to get me x. This is actually going to get me x cubed. So I've got like an x to the 2i. And then there's going to, again, I may have a plus, well, I have to have a plus or a minus 1. All right. So it's about which one I choose. And the thing is, this is going to go on 2i. And so typically, what do? We usually go plus 1. So 2i plus 1. When I is equal to 0, that gives me this. When I is equal to 0, that's positive. So, all right. And so I've got these nice little things. Notice how, like this, if I sort of take away the alternating sign part, this is like the odd terms from my exponential function. Yeah? Cool. And so cosine of x, kind of the same thing except for shifted back 1. So it's going to start 1 and then it's going to have an x squared on 2 and so forth. Yeah. So I can actually go summation I is equal to 0 to infinity. And so it's got the alternating sign again, minus 1 to the power I. this is just going to be x to the 2i. When I is equal to 0, I need it to be equal to 1. Yeah? And so 2i factorial. So it needs to be positive when I is equal to 0. Minus 1 to the power 0 is 1, so we're good. That's going to get me 0. So I should be able to just use these to work out what I'm getting. So this should just get me x minus x cubed on 3 factorial plus x to the 5 on 5 factorial. Just check while I'm doing this. When I is equal to 1, that's going to get me x to the power 3. That will be 3 factorial. When I is equal to 2, that becomes positive again. This becomes 5 factorial. Sweet, that's going to work. When I do this one, I is equal to 0, that becomes 1, that's 1, and that's 1, so that is literally just 1. And then when I is equal to 1, that's a negative x squared on 2 factorial, and then I is equal to 2 gets me x to the 4 on 4 factorial, and they kind of go on. Okay, whoops, it's terrible focus there. That way. That way. Good. Okay. So there, if I add these two together, I actually, well, no, if I add the absolute value of these, I'd get that thing going. All right. So you can see that they're related to, and we're expected to know that. The next one that we're expected to know is, do we know what? There's only one more that we expect you to actually know. So there's a couple of, actually, there is one thing that's actually obvious that we probably did say, but you may have missed. Have you ever thought about doing a Taylor polynomial of a polynomial? No, sounds like a stupid idea. But, what's that? Well, the thing is, like, the Taylor polynomial of a polynomial, if my polynomial is degree 5 and I do the degree 5 Taylor polynomial or higher, it will be exact. It will be the same thing. And it's kind of obvious when you say that. When you think about it, it's kind of go, oh, if I do a 5-degree polynomial, to be a polynomial, because Taylor series says in the limiting case, as n goes to infinity, it will be exactly that function. What we're saying is, okay, if it's a polynomial, it will just be that polynomial. That's all that's going to happen. So there are some functions. So if you think about the functions we have like the trig functions, we have log and exponential functions. Really, we don't have a lot else that we talk about. You know, there's the polynomials, and then everything is built up from those. Okay, and so the only one that we haven't actually given an actual answer to would be like ln of x. And so again, so when I'm doing a Taylor polynomial, so you've noticed what I've done here. I've written out the function and its various derivatives, and then I've evaluated that function at 0. With the log function, we tend not to evaluate at 0. We've thought about that for a second. You kind of go, yeah, okay, that makes sense, doesn't it? Because it's going to be terrible at 0. So quite often what they'll do is they'll actually go ln of x plus 1. All right. So they'll get an approximation for ln of x plus 1. If we do this, all right, so the first derivative would be 1 on x plus 1. And then the second derivative would be minus 1 on x plus 1 all squared. And then 2 on x plus 1 cubed. So this is a little bit more difficult to work out what's going on, isn't it? But if we look at the pattern, the next one I'm going to times by minus 3. So I'm going to have an alternating sign. I'm going to have, this is like, it's like a factorial on the top there. And this thing would be x plus 1. And then it'll be like, so this is where we go, hang on, what makes it work? All right. If I do I is equal to 0, this is not going to get me the right thing. So if I take I is equal to 1, I want it to look like this. All right. And so that's where I might go plus 1. And this should just be I. And so this thing here actually should be I minus 1 factorial, all right? I look for the patterns in there. I can see that at every step I'm timesing by the next integer. And so I can write it like this. And so I've actually got a general form for this. And the reason, so like its derivative as a function of x is going to be that. So my nth derivative evaluated at 0 is going to be minus 1 to the I plus 1, n plus 1, that would help. And then n minus 1 factorial on, this is going to be 1. It's just this top line. So when I put it into my Taylor polynomial, so ln of x plus 1 is equal to some I is equal to 0 to infinity. So this is kind of interesting. When that first one evaluates to 0, when I put in x is equal to 0, I get 0, right? When I put in x is equal to 1, for the first derivative, I get 1. So in actual fact, quite often what we'll do is what's that? Oh, thank you. So when I'm evaluating it at 1, I can actually sort of skip that first term because it's 0, and it can make my life easier not having to try and fit that into a summation formula. And what I'm going to get is like minus 1 to the I plus 1, and then I plus 1, I minus 1 factorial, and then n factorial, and I factorial, this is the problem. And then we're going x to the n, all right? And so when I simplify this thing here, I actually get minus 1 to the I plus 1, x to the n, x to the I, that should be an I. I'm going to get there eventually, on I. So this I minus 1 factorial on I factorial just leaves you with an I. And so again, we're getting, it's different from the series that we've got, but it's similar sort of thing. Actually, maybe I will try and write this out. Summation n is equal to 1 minus 1 to the n plus 1 x to the n on n. All right. Okay, so these are some standard ones. These are some, whoops. Let's try that again. Let's just go to focus a little bit. Okay, sure. Why did I bother doing that? there was actually a reason why I bothered doing that. All right. So we're in the exam, they may actually go e to the x squared. All right, Taylor polynomial for e to the x squared, or Maclaurin polynomial. Now, this is like e to the power f of x, where f of x is equal to x squared. So it's a composition of functions. All right. Do we know why I'm doing that? Actually, it's actually not well explained in the notes, but because e to the x is equal to, what did I write down? Summation n is equal to 0 to infinity of x to the n on n factorial, I can actually say that e to the f of x is equal to some n is equal to 0 to infinity of f of x to the n on n factorial. Hashtag, this is not entirely true everywhere, all right? But what this means is that e to the x squared, I can just go, this is just going to be summation n is equal to 0 to infinity of x squared power n on n factorial. All right, do we love the plan? So sometimes what you're going to do is you're going to recognize these things. You can go, oh, this thing is this composed with this. It works for compositions. We've got to be a little bit careful if we want to talk about products. Like in principle, I could do e to the x times sine x, right? But that's like if I treat that as a sum and that as a sum, then it gets really, really confusing. So if I was to just sort of do the same thing, all right, I can, technically it's true. So if I do e to the x times sine of x, technically that would be summation n is equal to 0 to infinity x to the n on n factorial times by summation n is equal to 0 to infinity minus 1 to the n x to the 2n plus 1 on 2n plus 1 factorial. All right. The reason we don't tend to do that, you can, but you don't, is this is going to be something like 1 plus x squared on 2 plus x cubed on 6 plus dot dot dot. And this one is going to be like x plus x cubed 3 factorial plus, minus plus x to 5 on 5 factorial plus. So you can see I could actually do this. This would suck. All right. Because you're going to get that, but then that times by x, and then that times by x squared on 2, and so on and so forth. And so I could actually use it to work out the first few terms, but I wouldn't want to use it to work out the whole series because it's too complicated to work out what some of those components. Like if you look at x cubed, like I get an x cubed by timesing that one and that one and that one and that one. So there's only 2 values. But if once I get to like x to the 7, there will be half a dozen things that I've got to add up, and so it's too difficult to do. In principle, it would work. In principle. Okay. So, all right. I've got to learn to count. Okay, so that's how we're doing this. Next thing we're going to do is, having found a Taylor polynomial, we want to use it. All right. So we want to know how to work out where these things are. So if we just take my formula for e to the x and go, what's the radius of convergence? Do we know what the radius of convergence is off the top of our head? I have this feeling it's 1, but let's do it and find out. So because my series is, so e to the x is equal to this, which is x to the n on n factorial, then my ratio test, would be like limit n goes to infinity of, so this will be like x to the n plus 1 on n plus 1 factorial times by, so I'm going to divide by that, but because it will make my life easier if I write it as a ratio, I'm multiplying by the reciprocal. All right, and we know that's going to be like limit n goes to infinity, and I am going to have my x to the n, and my x to the n plus 1 is going to give me x, and my n factorial is going to give me 1 on n plus 1. Now, this is equal to absolute value of x, limit x goes to infinity of 1 on n plus 1. I can take the x out because it's not dependent on n. It's like a constant with respect to n. What's the limit of that thing? Sorry, n. That's supposed to be an n. So if n goes to infinity, that term goes to 0, doesn't it? So this is equal to 0. Less than 1. Strictly speaking, it converges for all values x in R. All right. So if I take any number x I can get my Taylor polynomial will give me exactly that because Taylor. So I kind of glossed over the thing, but there is a thing that says the Taylor polynomial. We can, so Taylor's theorem. Um, f of x is equal to, and it's equal. So it's equal to that. The it's actually an equality. And so it's saying it's equal to, and my radius of convergence is saying that's true for everywhere. The only problem is the further I get away from the center, the more terms I have to have for it to converge. All right. So the further away I am, the more terms. And so, that's what we do with Taylor polynomials. What do we do with Taylor polynomials? So as you get, so this would be considered a numerical technique, right? So it's a way of creating a sum. Your calculator, I don't actually, I'm pretty sure it still does, but calculators originally used a Taylor polynomial, about a 15-degree Taylor polynomial. But to do sine, cos, tan, etc., they used a Taylor polynomial. And so this will always be exact, okay? There is some other tricks if you want, I can talk about that, but the short version is they will be exact. So the thing is, we want to know how accurate. We always want to know how accurate it is, okay? And so that accuracy comes from my error term. So so in actual fact, if you do anything with sort of numerical techniques, the first thing you talk about is the error term. And so we got told that the remainder term, Taylor actually showed the remainder term as a function of x is actually the nth plus 1 derivative evaluated at some z. And so n plus 1 factorial x minus a to the n plus 1. All right. The statement z is between x and a. All right. So we don't necessarily know whether x is greater than a or less than a. We just know z lies between x and a. So the thing is, you're going to get you will almost certainly get asked to calculate an error. All right. Or how many terms do you need to go for your error to be for this one? So maybe I don't know. So find n such that the error for e to the 0.4 is less than, I don't know, 0.001. All right. And so what we're going to do is we're just going to go, well, what is this thing going to be? All right. And I've done something reasonably easy just to demonstrate the process. All right. But this is like a question that has been in the exam before. All right. It's definitely, it was in your assignments. Do you remember seeing that in your assignments? Yep. So you know what you're going to do is you're just going to take this thing here. Because I'm talking about e to the x, my nth derivative is just going to be e. It's evaluated at z. All right. This is like n plus 1 factorial. I'm just going to go a is equal to 0 to make my life easier. All right. Now, that would be my remainder as a function of z, as a remainder function of x. So my remainder at 0.4 would be e to the z, and then 0.4 to the power n. That should say plus 1, shouldn't it? Okay, sweet, that thing. Okay, now, what I'm looking for is a bound. All right, so I'm actually looking for the absolute value of that. And so I want to know something, I want to find I want to find an m. I want it to be as close as I can, but actually I'm saying that's less than 0.001. Someone's turned up. Sure. And so I'm going to be able to go, all right, ideally I'm looking for that. There is no change of signs. So the thing I'm going to do to work this out is I'm going to work out what's the maximum value. All right. Now, this e, I've got e to the 0, and so this should be, my e is actually an increasing function. And so because I'm between 0 and 0.4, my maximum value is going to be at 0.4, which wasn't a great plan. But anyway, we're going to do this. E to the 0.4, 0.4 to the n plus 1 on n plus 1 factorial is less than or equal to less than 0.001. Now, that's a bit of a problem. I've got a little bit of a problem in that I'm actually using the function to estimate the error. So what I'm going to do is I'm going to make an assumption about that value. All right. So if it was 0.5, it would be like the square root, and the square root would be less than that. I'm actually going to replace e with 3. All right. So I'm actually going to go e to the 0.4. I know is less than 3. All right. I can, in this situation, I'm allowed to go, it would be the square root of of e. It would be less than the square root of e. And so I'm actually just going to go, let's choose a value which I know currently covers it. All right. And so that means I can replace this term. So I've got 3, 0.4 to the n plus 1 on n plus 1 factorial. Now, at this point in time, I'm going to make some guesses, right? This is not, I'm going to go equal to 0.001. I've got an n plus 1 in the power and in a factorial. That can make my life difficult. So I'm actually going to guess. All right. I'm actually going to go do a bit of a trial and error thing. So if n was, so because this is 0.4 and this is 0.00 something, there's like about 1 in 1,000. If I do 0.4 times 0.4, it's going to be 0.16 times by that would be 0.064. Do it again, 0.0025. So somewhere around, I want my n plus 1 to be about 5. All right. Now, I'm actually going to I'm going to get lazy on I'm just going to do that. And so, wrong thing. What I want to do is I want to do that one. All right. What I'm going to do is I'm going to do, this is going to be n, and then this is going to be the remainder. All right. So I'm going to do 1, and then this is going to be equal to that number plus 1. And so I can actually generate some values nice and quickly. And I said it should be 3 times 0.4 to power that number. Oops, I've got to say equals. That bit's going to be that number divided by. All right, and so I kind of got lazy because I wanted to go, so my n plus 1 needs to be equal to 5. So I wanted to do the calculation quickly, which is why I've done Excel. You can actually do a similar thing in your graphics calculator. Do you get to use graphics calculator for the game? So this is where, did you see me when I was doing this? I'm going to say I just did powers of 0.4 in my head, which you can do, right? When you think about what's actually involved in doing that, it's not actually that hard, right? And that got me to, I want my number to be about 5. And so if I was doing this in the exam, I would have tried, I would have started with n is equal to 3, n is equal to 4, n is equal to 5. The second one would have been the right answer, all right? So I would have used a little bit of understanding before I went through and changed got myself the answer. All right. So I can actually do this. So this is one of those things. They're almost for every 1B exam, there's almost always something that involves a Maclaurin or a Taylor polynomial. Things like radius convergence are in there. All right. Also something almost always something that involves the error calculation. All right. That's why it's an important thing to look at. This is, this is slightly different from one of the things. The one thing that most people don't expect to see is that composition of functions thing. And that occurs reasonably frequently for Taylor polynomials or Taylor or Maclaurin polynomials. And it's true, right? Because f of x is equal to that sum. If I do an f composed of g, that sum composed with g is the same function. All right. And that's one of the things that can save you a lot of effort. All right. Because, and similarly, like if I was to do, and it was actually in someone's Mobius this year. Literally, that's going to be x squared times by the sum, x to the n on n factorial. You can actually just go, hey, this is you can actually say that by the same reason, all right? It gets difficult when I want to use Taylor polynomials for two different functions, but when it's just multiplied by a polynomial, it's nice and simple. Okay? Do you guys got questions about that? Is there something you want me to talk about in particular around that? Characteristics of subspaces. Characteristics of subspaces. Sure. I feel like now is a good time to do that. For the person who's online, if you pop questions in the chat, they will pop up and they should see me. I should see them. Subspaces. What do we know about subspaces? You guys know lots of stuff about subspaces, don't you? Yeah. One of the things that we've got to sort of put our mind into, how did we come up with this idea? All right. There's a certain amount of, this seems like a way out idea. And what actually we've done over many years is step back and go, what is it about that system that makes it work? All right. So when we're talking about spaces, we're sort of going, hang on, what do we mean by a space? All right. And so we kind of go, there's like a conceptual center, which is where that zero comes in. In actual fact, that goes from a slightly different point of view. That comes from the idea that that there is an inverse. So every element in my space has another element that I can add to it to get back to zero. So it's like an additive identity. All right. So I add zero to stuff, it doesn't move. All right. So zero is a special thing. We like that. Everybody loves zero. Zero is one of the world's greatest inventions or observations. So we want our space to have that sort of property that I can add something to something else and get back to where I started. All right, that inverse. Each element has its own inverse. But then we've got this thing for a space where if I keep on adding stuff, if I add two things in my space, it's just something else in my space. All right. Kind of seems a little bit obvious. Like when I add two numbers, I always just get another number. I don't ever go outside the numbers when I add numbers to it. And so we're going, actually, that in itself is a property that we love. All right. So if we think about a space, you add points in 3 dimensions, you just get another point in 3 dimensions. Seems like a great idea. We want that thing. And so that's where we say we're closed under vector addition. All right. So we're going to do So vector multiplication, like multiplication by a scalar, is really vector addition by that scalar number times. All right. And so we actually also want it closed under multiplication by scalar. So all right. So the multiplication by a scalar thing means I can go any, and so these are the things we want. All right. And so that's actually the thing we're going to look for. The real problem with subspaces, most people's problem isn't with these particular properties, right? Most people's come down to how we've defined the set. Okay. So when we're talking about is this thing a subspace, we give you we describe a set of values in a certain way, and then we're going, but it is this thing in the set, or what does this set look like? Because we're giving you a set of points. So a straight line is a set of points. Is a straight line a subspace? So yeah, it's a trick question. The correct answer is it's a trick question, Nick. I can't tell you with that information. I need one more piece of information. What other piece of information do I need for it to know if a straight line is a subspace? Okay. The zero vector. Does it go through the origin? So this is like, so we go, straight line through the origin is a subspace. I'm going to do this. Gets its own special color because it's a problem. It's actually really important that we remember that zero is its own subspace. It is a dimension zero subspace, but it's still a subspace. Because if you take the set with just zero in it, it contains zero. Woohoo, I'm done. All right. If I multiply that zero vector by a scalar, it's still zero, so it's still in the space. It's still in that set. If I were to take two vectors which are in the set, sadly, there's only one vector in there, so I'm going to take zero and add it together, and I'm going to get zero. So it is technically a space, all right? And it's really good to get used to the idea of being a bit of an ass, really. Being that person who goes, oh, can I break this with a really simple example? Will zero break this? Will one break this? And so you want to, like, a lot of mathematicians will just think about the simple case that will break it, because that's actually a really useful way to do this, all right? Really useful way to do this is, can I think of a simple case that will break it? All right, so there are things that we know are spaces, straight line. So this extends out to planes, all right? Plane containing the origin. The reason I say, what's the simple thing that breaks it, is if my straight line is offset from the origin, all right, firstly, it doesn't go through there. If I was to include it, then if I take this point and add them up, I'm actually over here. I'm not on that line anymore because I'm displaced from the origin. All right. And so I don't do that. Same with the plane. The plane is basically the same idea, and sort of hence, hyperplanes that contain zero. All right. So that's equation. So set of vectors x1, x2, xn such that a1 x1 plus a2 x2 plus an xn is equal to 0. All right. So if I have this thing where if it's equal to zero, and like if I have this, this would be a linear combination of values and it's equal to zero, then that gives me a space. All right. So if everything in my space can be written as this, all right, it satisfies this equation. So x as points rather than vectors, then I know it's going to be a thing. So this is, yeah, in a really, really simple way, this is like the simplest form of a system of linear equations. So if I was to do sort of something that was like have two systems, like two, if I have like a1 x1 plus a2 x2 plus da 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 a n x n equal to 0, but then I had like a b1 x1 plus b2 x2 plus bn xn equal to 0. Is that going to work? So there is an answer that we should know. All right. The answer is yes. All right. So this, so set x1, x2, xn in Rn is a subspace. Why is that? So this is solution to homogeneous. All right. Now, specified homogeneous. We're all cool with the homogeneous, meaning each equation is equal to 0. Yep, cool. So my system of like, so it doesn't actually matter how many of those. So one you kind of go, okay, that makes sense. If I'm doing this, all right, geometrically, this is actually the intersection of subspaces. So okay, so I can know that this I've actually gone. There's actually one more piece of information. All right, what is the intersection? So we've said the intersection of these particular things is a subspace. Is it always true that the intersection of subspaces is a subspace? And the answer is yes. Yes, it is. All right. So, so we're going to go, it is always true. Mm, that the intersection all right. Now, okay, we're going to pause here for a second and go, hang on, how would we do this? Someone was actually asking me this last week. How do I show this? Okay, so the plan is always, well, more or less always the same. All right. If I think it's a subspace, all right, then I should be able to go, I should be able to show that it is. All right. So let U and V be subspaces. U intersection V is also a subspace. Okay. So 0 is in U and 0 is in V as they Therefore, 0 is in U intersection B. All right, so this is one of these techniques for showing something like this. The intersection means it's in both sets. And so I can get away with going, I want to show it's in that set. Then I just need to show it's in this set and that set. All right. So this is brilliant. Now I'm going to go, if we go let X and Y in U intersection V, X plus Y is in U, as U is a subspace. Seems like a bit of a cheat, but we know since it's a subspace, if I add the two vectors up, they should be in the subspace, right? In the same way, in literally the same way, same. Therefore, X plus Y is in U intersection V. All right. So I've got this, I can just keep doing this. This is kind of, yes, it is a bit boring. Yes. But that's the sort of thing I've got to do. So to show something is a subspace can be real tedious. All right. We've got to say all these things because they're expecting you to say these things. All right. If they ask you to show that it's a subspace. So intersection is a subspace, intersection of two subspaces is a subspace, everybody loves it. So if I go back a step, so you know how like there is all these things that are not. All right. So using the things that are, we can talk about the things that are not. All right. So you know the Mobius question, which is like which of these is are subspaces? All right. If you think about that, we have a gut feeling about it. All right. And so we can there were some which were system of linear equations, subspace. There's one that was the zero vector subspace. All right. Some of them straight line subspace. All right. Excuse me. Have we thought about what how do you write a line in multiple dimensions? What's the equation of a straight line in multiple dimensions? Ever seen that? We should see that. That should be, I mean, like actually it's one of those things we covered that actually in like math spec or 1M, depending on which one you did. And so L is a line and it goes through P plus T times a direction. All right. So that's the general form of a line. All right. L is if P is equal to 0. All right. So equivalent to saying it goes through, it contains 0 is to say that that P is 0. It's actually a little bit more complicated than that. There's one of the examples that's in the Mobius question that goes, they go 2, 4 plus 1, 2 times by T. That, because there's a value of T is equal to -2, that makes that equal to 0. So if T equals -2, 2, 4 plus 1, 2 times by -2 is equal to 0, 0. So it contains the origin. So it's P is equal to 0 is not the only way, but you've got to, if I'm recognizing that this point is a scalar multiple of this direction, there will be a value of T. They may do something tricky like that, but in general. So if P is equal to 0, this is just T times some vector. So do we remember what the definition of span is? What's it? No. Ha! No. Span is actually a shorthand. All right. So a lot of the problems with sort of this basis this space talk is actually the grammar of the situation. It's actually trying to say the things in the right way. Okay, and so a basis is a set of vectors which is linearly independent and span. In actual fact, there should be a little bit more in there. A basis is a set of vectors contained in a space such that those vectors are linearly independent and span that space. All right. So we get a little bit sloppy with that because we don't often specify the vectors that are in the space. It's kind of implied, but it is actually one of the, like I tend to think of that as the zeroth condition of a basis. All right. So, and they'll do that to you. Is such and such a basis for your subspace? And they will literally, like, definitely in exams I've marked, there has been which of these is a basis for this subspace? And one of them had two vectors that were linearly independent. Those vectors weren't both in that space. So it's not a basis. All right. We could see the space was dimension 2. I need two vectors. These vectors weren't both in this thing. So there's actually, like, we can sort of try and trip you up by going, they've actually got to be in the space and be linearly independent. And span is a horrible thing. Like showing vector span is actually kind of difficult. If I give you an arbitrary space and say, do these vectors span the space? It's kind of difficult. Except for if I can show they're linearly independent and the right number of vectors for the dimension of the space, then I can say they span. So, so my point is that, so if I have W, which is equal to span of some set of vectors, V1, V2, Vn, W is a subspace. Okay, so those are things that we know are. So I can look at the way the thing is defined and go, must be a subspace. There are things where we know where it's not. All right, so one of the classic ones from the Mobius, X, Y, X, Y. This set is not a subspace. All right, so it contains 0. But now I'm confident that it's not. So I'm not going to try and show that it is because that's tedious. All right, I'm going to show that it's not by giving one example. So the beauty of showing something is not a subspace, subspace, is I just need to show one of those conditions is broken by an example. All right, because it has to be true for all possible. If I show one where it breaks it, that's going to be enough for me to go, okay, not a thing. And so in this case, if I just pick a vector that was 1, 1, 1, let's call this U. That would be in U. Yep. What could we do to show that it breaks it? Oh, yes, do that. I've got it contains 0, so I can't do anything with the 0. I've got multiplication by scalar or vector addition, so I could pick another vector and add it to it. So if I was to pick another vector, if I go 1, 2, then this thing says that element's got to be 2 to be in U. But if I add this, if this is my X and this is my Y, X plus Y is equal to 2, 3, 3. But this number has to be this times this. And so this is not in U. And so therefore U is not a subspace. Okay, so when I've got something, I can go picture what it is. Now, the other one I want to talk about that's really common in the Mobius, let's see, what was it? Oh, how do they write it? I'm trying to think how they actually write it. Oh, that's right. It's like um, uh, x minus y times by z. We should try that again. X, y, z in R3 such that x minus y times by z equal to 0. Right, on fire. All right. Probably a clear indication that we need to pause for a little bit. But so this thing here, so geometrically, all right, we know what we're doing here. This is like z is equal to 0 or x minus y equal to 0. All right. Now, we love this one for one particular reason, right? So 0 clearly in there. Ooh, we're done. All right. If I do vector addition, all right, can you give me one vector that would be in that set? How about, I don't know, so I've got maybe 3, 4, and 0. Make that. All right, that's definitely in my set. Let's call this set V. And so that is in V. Definitely in V, because 3, 4, that's minus 1 times by 0 in the set. If I multiply that by k, I'm going to just use k. So this we're going to call x. Kx is going to be equal to 3k, 4k, 0. Still in my set, because this is going to be 3k minus 4k times by 0, which is equal to 0. So it's in the set. Okay? All right. Well, I did this one. Let's try something that does that one. So if I do, say, 2, 2, and 7. So if I take y is equal to 2, 2, 7, again, I can go, well, that's 2 minus 2 um, times by 7, which is 0 times by 7 is equal to 0. It's in the set. Woohoo. All right. If I do the same, what's that? Yep, sure. And so if I do the same thing again, if I do k times y, that's going to be 2k, 2k, 7k. And so it'll be 2k minus 2k times by 7k. Still going to be 0. So it's in the set. Tick, boom. This set is closed under vector addition, closed under multiplication by scalar. I'm now going to add my two vectors. I'm going to go x plus y. X plus y is equal to. And so this is going to be 5, 6, 7. Almost like I planned it, which I completely did not. So if I put this in, this is going to be 5 minus 6 times by 7, which is equal to minus 7, which is not equal to 0. Bum, bum. What happened there? So geometrically speaking, this is a plane where z is equal to 0. And this is a plane where x is equal to y. So, x is equal to y, so that way. And so what we're actually doing is this set is the union of the two sets. All right. And so it's useful. So same as knowing things are subspaces, knowing some things are not is useful, and being able to recognize that thing. So recognizing that this, so the key word here is actually this or. This or, when I wrote it out, that was the thing that said, like the first time I saw that question, and when I wrote out, I'm like, I don't know what to do. I would normally factorize and go, well, if that's equal to 0, that's equal to 0, or that's equal to 0. The moment I said or, I thought, that will be what breaks it. That is rather than intersection, it gives you a union. All right. And union of subspaces, not a subspace. Lines that don't go through the origin, not a subspace. Planes, etc. All right. And so system of solutions to system of equations, which are not equal to 0, not subspaces. All right. They're very like subspaces. Seems a little bit odd that this thing here away from 0 is not a subspace. If I move it to 0, it makes it a subspace. but it gives you that property of being closed under multiplication or scalar multiplication and vector addition. So it's really an important part about this. So it's good to sort of have those things in mind. All right, is that what you were looking for? And so if we go a little bit further, you know how we say the kernel of a linear transformation? Kernel is the set of all solutions to a homogeneous system of equations. And we've just said that's a subspace. So we know the kernel is a subspace. All right. And in actual fact, the range, because the range can be expressed as a span of vectors, literally those vectors is a span of the columns of the standard matrix for a linear transformation. That means it also must be a subspace. All right. So we say those things, and I'm sure the lecturer actually probably did tell you exactly that at the time, but we can know these things are, and that means we can exploit some of those properties of knowing that it's a subspace. All right. So the possibly the other things. So this was an example where, like, if I looked at that, that would be like xz minus yz is equal to 0. This is where we got what we'd refer to, whoops, let's put it up there. This would be what we refer to as cross terms, the two variables multiplied by each other. So if I have a situation where I have sort of any power other than 1 or 0 of my variables, or I have the product of variables, that inevitably means my space that means my set is not a space. There is the classic exception, all right? The exception that they always put in, and if we go back to my first thing, this. All right, I can write the set that contains just the 0 vector in a lot of ways, all right? And I can choose, because it's only 1 point, I can choose to do this in lots and lots of ways, all right? So the one they did in the Mobius is where if I go a set of all x, y in R2 such that x squared plus y squared is equal to 0. This is where the reason we do this to you is we want you to think, like, normally if you go, is that a subspace? You go, no, all right, because I see x squareds and y squareds. It's not a subspace. But when I put that next level of thought into it, there's only 1 point that satisfies this. This is equal to the set that is 0, 0. That is all that it's equal to, and I know that set is a subspace. All right. So there are lots of ways I can say 0. And so if you see something and go, hey, that's a bit too easy, ask yourself, does it contain, like, the first question you're going, does it contain more than just the 0 vector? All right. It can be a bit of that next level thinking. But these ideas where you recognize what it is and know which way that's going to go, you can sort of help save yourself a lot of time with showing whether it is or not. All right. Is this a subspace or not? Depending on whether what I think it is really important to determine what happens from that point on. Okay. Anything else? That's okay. What's that? Projection. Oh, awesome. So what is the trick with projection? So if I'm trying to do a projection, so the formula for a projection is like, so if I'm doing the projection of x onto y, where these both are just vectors, reasonably simple. X dot with y times by y, all divided by the length of y squared. All right, let's pause for a second. Why am I dividing by the length of y squared? What's that? Well, yeah, so my projection shouldn't change depending on the length, the value of the y I choose, right? So if I choose 1, 2, or 2, 4, the projection should be the same because those are in the same direction. All right. And so if you think about it, this dot product has a factor of the length of y in the dot product, but also in y. All right. So when we come to doing a projection onto a space, and so what I want to do is I want to make sure that I don't have this problem with the length thing. All right. And there's also one other factor is I don't want, like, if my basis vectors that I'm gonna have to have something to project onto. I want to sort of add up all these bits, but I want to use a basis for that. And so the thing I want is I want to have an orthonormal basis. So what we're going to do is we're going to go let my V1, V2, Vn be an orthonormal. Okay, so by making it an orthonormal basis, all right, I'm alleviating some of this having to divide by the length, okay? And so that's one of the things that makes my life really a lot easier. Okay, so formula, so is just equal to, so it's like x dot v1 times by v1. So it's basically when the length of v1 is equal to 0, I can ignore that bottom part. And I'm just going to sum the components. Yeah. So we're used to sort of, if I have like x, y, z, that is just x times the vector 1, 0, 0 plus y by 0, 1, 0 plus z by 0, 0, 1. Right? We're used to that. Yeah. But if I want to write it in a different basis, right? So if I give you an orthonormal basis, there's a unique representation for everything. And in actual fact, this kind of gives away what that representation is, all right? So if x in W, so if it's in W, then projection of x onto all right. So this is actually one of the things that is sort of, it kind of makes sense, but and we will use that a bit, is to go, if I do the projection of a vector and it's equal to itself, then that vector must be in the space that I'm projecting onto. All right. And moreover, so therefore, x can be written, x is going to be equal to like C1 V1 plus C2 V2 plus dot, dot, dot. So if it's in a space, it can be written as a linear combination of the basis vectors. But this thing here tells me one more piece of information. It's actually telling me that C1 is equal to x dot V1. And maybe I should do CI is equal to x dot VI. It's actually telling me those coefficients. All right. So I can actually, if I want to write a vector in a different basis, so in my standard basis, really easy. But if I want to write it in a different basis, all right, I get it has to be an orthonormal basis. And so I can actually work out what those coefficients are just by doing the dot product with each of those basis vectors. And when you think about it, that's kind of super cool. At least I think so. When you sort of see how that's working, it's just like going, actually, the bit in that direction is just found by doing the dot product with that vector. And you think about, and it applies here. If I did that dot with 1, 0, 0, I would just get X. If I do that dot with 0, 1, 0, I just get Y. So you can, it kind of is, what I think is cool about it is it works in the way you feel would make sense. So that's why I think it's actually pretty cool that it works the way you expect it to. Yeah. All right. Cool. So projection leads to Gram-Schmidt process. All right. David has done a thing. David loves his. Have you ever seen the kid show The Fairies? Right. So in Fairyland, there is only one way to tell the time. Blah blah blah. And there's the song. I don't know the song. My kids weren't into the fairies. There are great things. David, however, will do the song if you ask him. But the short version is project, subtract, normalize. All right. So if I'm going to Gram-Schmidt process can be summed up by the idea of I take a vector. I start with a vector and I'm going to normalize it because I'm going to do a projection. I'm going to get the new vector that I'm going to add in. I'm going to project it onto this bit. I'm going to take away the projection. So that creates the orthogonal component. And then I'm going to take what I've got left and I'm going to normalize. I'm going to make it length 1. And now I have 2 vectors that are a basis for a component of the space I'm in. And so I take the next vector for the basis. I project onto the current basis. I take away that projection, which gives me the orthogonal component. And then what I've left, that orthogonal component, I normalize, make it length 1. So if we think about it from that point of view, like if you look at what we do, so if I start with, so basis U1, U2, I'm just going to go U3 to make my life easier. All right. All right. That looks terrible. So this is just saying V1 is equal to this. So V2 dashed is going to be U2, but I'm going to take off the projection of U2 onto, so I'm going to take off the projection. So it's going to be like U2 dot V1 times by V1. And this bit, so V2 dashed will be perpendicular to V1. All right. So I'm going from basis U, which is not necessarily anything other than a basis, to a basis V1, V2, V3, which will be an orthonormal basis. And so this bit is made this thing length 1. And so then I go V2 is equal to V2 dashed on length of V2 dashed. All right, normalize. So that's not going to fit. Dot, dot, dot. We'll let you fill in the blanks. And so then I do the same thing. I do a V3 dashed is equal to U3 minus. And so this is where the projection comes in. I'm doing U1 dot V1 times by V1 plus U2 dot, so U3. I did that there. Yes, did that. Beautiful. 2 times by V2. And then V3 is just V3 prime on V3 prime, the length of V3. So one of the other things that can be really helpful when you're thinking about vectors is thinking about what the property of the vector is that you're interested in, okay? So I actually got told a lot of times when I was in first year by my friends that you can't do that. All right. So if we think about what this is, this normalization process, this is multiplying by a constant because the thing I want is that direction. So I've found V3 dashed is the right direction, but not the right length. Okay. And I'm about to times by a constant to make it the right length. Okay. So if I think about what component is I want and what I'm trying to get, I can save myself a bit of effort. All right. By going, actually, the direction is the thing I'm interested in, I can forget about the length. And that means I'm free to multiply by any constant I like. And specifically, I can multiply by a constant that will make it so that the next step of the calculation is easier. All right. So when I do the Graham-Smith process, quite often you'll find I will multiply VP prime by some number so that all of the values are integers. And then dividing by the length becomes easier because if you've ever tried to work out what the length of like a half and 3/4 and 5/7 is as a vector, that's a horrible thing. Horrible. But if I multiply by the right number, I get integers and it's like Pythagoras theorem. Like, oh, okay, so square root of that number. It makes the next step of the calculation easy. And so if you think the direction is the thing I'm interested in, I can multiply by a scalar to change the length, but not the direction, then I can make my life easier. All right. And so this can actually apply to even at the step where I'm actually creating the original basis. Rather than having bases with fractions in them, I can make sure that they're whole numbers and make that step of the calculation easier by identifying whether it's the direction or the length or both that I want. With the Graham-Smith process, I fix the direction and then I fix the length. All right. And if you think about it from that point of view, so the normalization, so taking away the projection creates a perpendicular vector, gives me a vector in the right direction, and then I'm making the vector the right length. That can help you think about what you're doing. Okay. And almost always, under like Taylor polynomials, almost always there is a question which will require doing something about the Graham-Smith process. All right. Usually they put it on the back of an eigenspace thing. So where you create an eigenspace of dimension 2. And so they'll want you to do enough of the Graham-Smith process to create an orthonormal basis for that. Okay. More questions? Well, I was going to say with about 10 minutes to go, we could finish early, or we could. I'm happy to go till like 1:30 when David comes in for the next one. But also, I'm happy to go. I've talked for like over 100 minutes. You may want to rest from my voice. Column and row space. Oh, this is actually a really good thing. Yes, good work. Well done. Where did I put mine? Okay. Okay. So the first thing we're going to remember is we're saying space. All right. So both the column space and the row space are defined as the span of whether it's the rows or the columns treated as vectors in the appropriate space. All right. So column space is actually the one that's a bit tricky. All right. So if you think about row space, nice and easy, rows of 8. Right. So if row reduce. So the row space is easy because if I row reduce my matrix, row operations don't change the row space. If you think about what a row operation is doing, I'm either swapping the order, I don't care. I'm multiplying by a scalar, don't care, because the thing about a basis is the direction that's important. All right, so the direction, so for a basis, length of the vectors is unimportant, unless I'm talking on an orthonormal basis where I want the length want to be one. It's only the direction that's important, generally speaking. And so what that means is I can just go, I don't care about the direction per se. I don't care about the length. And so multiplying by a scalar, not going to change it. Adding adding a multiple of one vector to another vector is like vector addition. All right. So, and we know that my space must be closed into vector addition. So the things I'm left with must be still in the space. I'm not changing the space that they're in. All right. And so then I can go, well, if I could have made, so if it's actually in a genuinely different direction, I can't use the other rows to make it zero. So any zero rows I can forget about. And so the non-zero rows form a basis. They must be linearly independent. And if you think about the row, that reduced row echelon form, because you have that sort of thing that looks like the identity that starts it, right? Because leaving one, I make sure there's zero above and below. Leaving one, zero is above and below. That sort of thing is going, hey, I can almost just see that they're linearly independent. All right. So I know they must be linearly independent. But column space is this problem. So if I row reduce, if I take my columns and I row reduce, if I get a row of zeros, that if we think about that first vector, all right, it's going to have a one, going to have zeros all below, right? But that vector had non-zero terms in there. So the original space was a scalar multiple of that original vector, right? Not necessarily zeros in any other row, in any of the other components. But when I take the row reduced vector, row reduced column, it's got lots of zeros. And so I may have zero components in those bottom parts, the lower ends of the entries, where there wouldn't be in the original space. Row operations change the column space. So, right, this is actually really important that we recognize that. All right. But there's a cool thing about the row operations is they still help identify the linearly independent columns. All right. So we should be aware that, like, unlike with the row reduction for row space, those vectors, there are infinitely many bases for any space, any sort of non-zero space, right? So so there can be any ones, but like the row reduced the row reduced form for the row space is kind of nice in that it's going to be one specific thing. There will always be exactly one of those for any matrix. All right. With the column space, I'm not getting, like, I actually have some choice about what columns I use exactly. All right. Because I could choose which pivot columns, but we know that the pivot columns will form a linearly independent set. All right. And so this is where, so for the row, for column space, all right, so I'm going to row reduce to find my linearly independent columns. All right. My point is there is some choice about, there can be some choice about which ones you decide to be pivots. You can actually, there is a little bit. You have to then go back. That's not right. So I have to go back to the original matrix and pull out those columns. And really, there is not much, there's not really that big a trick, all right? So anytime you're asked to find a basis of something, like it has to be, like you can't go blue, a blue bowl, a blue shirt, a blue, it has to be, the color is applied to a thing. A basis is applied to a subspace, all right? So if you're asked to find a basis, it has to be of something that is a space or subspace. And so that thing is the thing that tells you what you're supposed to do, all right? What is a basis for the kernel? Well, the kernel comes down to be the solution set of the standard matrix. Oh, I find that the process of finding the solution set of for a matrix or the null set gives you a basis. The way I'd write that out, like I row reduce, I assign three variables, parameters, write things in terms of vector times parameter, vector times parameter. That's actually giving you it as a span of vectors, and that creates a basis. The way we do that creates a set of vectors which will be linearly independent and span, so therefore it's going to be a basis just by creating it. If I'm asking about a row space, all right, I have to do the row reductions. I know I take the non-zero rows. If I'm asking about a column space, I know that that's the tricky one, all right? So the reason where column space comes up is the column space is the range of a linear transformation. Okay, so, and notice how we've been clear about, I'm saying, I don't say range of a matrix. There is not a basis of a matrix. There is like three things it could be for a matrix. I need to be specific about which one of those things, because that's the thing that we're being taught. A matrix is not a space. A matrix can be used to define a space in several ways, putting it as a linear transformation. All right. So that's why it's really important you decide what the thing is that you're being asked about. All right. And so again, this is why mathematicians get picked on for being pedantic, because we want to be clear about the thing that we are finding. All right. I can't find a basis unless you tell me exactly what space you want me to find a basis of. Does that help clear things up? Okay. Ooh, that's always tricky. The making up an example on the spot is difficult. All right, let's do the ubiquitous. 1, 1, 1, 1, 2, 3. I don't know. 0, 2, 1. I don't know. Actually, do I want it to be? I probably want it to be. If I just do 1, 2, that will make my life easy. That will give me a free variable. All right. And so, if I row reduce, so 1, 1, 1, and then 0, 0. So it's going to be row 2 is equal to row 2 take row 1. And so that's going to be 1, 2, and this is 1, 2. And so the next 1, 1, 1. Actually, I'm going to make that 0, 1, 2, 0, 0, 0, 0. Row 3 is equal to row 3 take row 2, and row 1 is equal to row 1 take row 2, and that should be minus 1. Okay, sure. And so I can go from this, I can go so my basis of my row A would be 1, 0, minus 1, and 0, 1, 2. You notice how I did this extra row operation? That could have changed the basis I used, all right? It would still be an equally valid basis, all right? All right, so this is where I've got a pivot here and a pivot here. And so that means I've got to go up to that column and that column. And so it's going to be 1, 1, 0, and 1, 2, 1. All right. Oh, thank you. Yeah, so I've got these ones. And so the last one would be, all right, and that would be taking my system 1, 0, -1, 0, 1, 2, 0, 0, 0, and making it equal to 0. The row operations would have, if these values started at 0, they would remain 0. So x3 is equal to t. And this equation says x2 plus 2x3 is equal to 0. Therefore, x2 is equal to -2t. This one says x1 minus x3 is equal to 0. So that's saying x1 is going to be equal to t. And so I'd write that as t minus 2t, t. I would actually take out the common factor of a t. Factorization is your friend, people. Anytime you can factorize, you should factorize. So just going to talk a little bit. Notice how I've tried to put squiggly brackets around my my thing. A basis is a set of vectors. The first words when we talk about the definition of a basis is a set of vectors. So I've used the curly brackets to indicate that I'm talking about a set, and then I'll put the elements of that set inside the vector inside. So you see up here, I've got my curly brackets. I've got my 2 elements of my basis. Okay, so that's how I know that I'm talking about a basis. It's a set of vectors that are linearly independent and span. Yes. No, if I'm saying it's a basis, it's implied. All right. So if I'm trying to describe a set, I can go a basis for this subspace is this, or I can say that that the space is spanned by this vector. All right, or such and such a space is the span of these vectors. Okay, so it's kind of up to you which way you go with that. Okay. Yes.
The original with the column space.
Yep.
The pivot columns that take you to the columns of the original height.
Yep.
Are they always guaranteed to be?
Yes, they are. Yep. So that's one of the beautiful parts about this. There is a thing where I could have kind of gone, I have a choice between using this one or this one. And so I could have chosen those two and it would have been the same thing. But I don't want to, don't confuse the issue. Just stick with the pivot columns. Yep. Cool. I think given David turn up for the next seminar, there's half an hour. I was going to say, do you guys got more questions or not? You can think of more questions if you try. So remember, this will go up on our website. So if you look at resources and then find Maths 1B, you will find not only this one, but you'll find, I don't know, about 2 dozen that David's done over the years. 2011. Yeah, it's going to say if you did one every time they taught 1B, that would be like 13 by 3, so 39. Everything should be covered by that. Okay. All right. Good luck with the exams, guys. And of course, you can keep asking us questions in the Maths Learning Center if you want as well. No worries. Now, where's the him? No. Stop that one. Stop recording.